All right, so the horizontal axis is the real, I had to turn on the recording so I could record for you. The vertical axis is the imaginary axis. So the y-axis is going to be like the I-axis, and the x-axis is the real numbers. So if we wanted to represent the number 2 minus 3i, we would go 2 to the right and down 3. And we can draw that as a vector. So P is the point. So we can represent complex numbers as vectors. And the sum of two complex numbers is represented by the vector that is the resultant of the vectors. So you're going to use a little bit of the vector stuff we learned last chapter. So if we want to add the complex numbers 4 plus I and 1 plus 3i, we know that we can just combine the real parts and the imaginary parts to get 5 plus 4i. This is what it looks like when it's represented over here on the coordinate plane.
That's where we get the weird parallelogram law or whatever.
Yeah, yeah, and you can hook tail to tail, but then the resultant has to go from the two tails to the endpoint of the other side.
Right.
Okay, so to find the sum of these two complex numbers is pretty easy. We just combine the real parts, which is 2, combine the imaginary parts, which is a negative 5i. Yep. And then that's what the graphical representation would look like. So most of this should look like last chapter, with the exception that we're now, instead of talking about the component form of vectors, we're talking about complex numbers, but the same idea.
Yep.
Okay, some relationships among x, y, r, and theta is that x equals r cosine of theta. And you maybe remember that from about chapter 4 or 5. We had defined the cosine as being x over r. So we just multiplied both sides by r. So
yeah,
you need to associate x with cosine and y with sine.
Yeah.
You just have to take the radius times that. If you draw a picture, it's really easy to come up with these two. And of course, r still is the square root of x squared plus y squared. It's been a while. And tangent of theta is still y over x. So we've had all of this before. They're just reminding you, and we're going to be using it with complex numbers, but we're still going to have an x, y, r, and theta.
Yeah.
So the expression r times the cosine of theta plus I sine of theta is a trigonometric form, or the polar form, of the complex number x plus yi. Now remember from the previous page, r times cosine of theta was x, and r times sine of theta was y.
Yeah.
So same thing there. So just the radius times the cosine of the angle plus I times the sine of the angle is the polar form. So the expression cosine of theta plus I sine of theta is sometimes abbreviated CIS theta. I never use that. That's not something I learned, but you might see that.
All right.
C is for cosine, and then I sine of theta.
All right.
Using this notation, r cosine of theta plus I sine of theta would be r CIS of theta. The number r is the absolute value, or the modulus, of x plus yi, and theta is the argument of x plus yi. You'll remember the magnitude of a vector. We use the absolute value symbols, and that's the absolute value is the magnitude of the vector form. Okay, so if we want to express 2 cosine 300 degrees plus I sine of 300 degrees in rectangular form, to get the x, we're just going to take r times the cosine of 300. To get the y, we're just going to take 2 times the sine of 300. So cosine of 300, 300's in the fourth quadrant with a 60-degree reference angle. And cosine is positive in the first and the fourth. So that's how they got 1/2 here. Just a little bit of review.
Yep.
And sine of 300 is a negative square root of 3/2. Sine's negative in the fourth. And with 60 degrees, sine of 60 is square root of 3/2. So we just take those both times 2, and we get 1 minus I radical 3. So that's in, this is called rectangular form here. This is like the form we used in 8.1. This is the polar form. So you can set up your graphing calculator to show polar form. We're going to do that in a few minutes. But here they've just put in the calculator 2 times the cosine of 300 plus I sine of 300. In your graphing calculator, you can change the mode. Let me see if I can switch to this real quick, because this will be helpful for you. Okay, are you seeing my graphing calculator?
Yeah.
It's
Convert.
pretty unfocused. I'm kind of rigged up a document camera that I could use. But I press the mode button. I can go down here to function. I can put it in polar form if I want. I can also change. You got to pick it up to be able to see it. And then right below that where it says real, I can also change it to A plus BI form. So that will allow me to put in A plus BI. So 2 plus 3. There's a couple ways you can get I. There's an I down here at the bottom. It's blue, so I have to use my second blue. And then if I wanted, I can convert that to, that's rectangular form. And if I wanted polar form, I could select that. And we could do 2, I can't remember, cosine of 300 plus I sine of 300, close both parentheses. And then math, enter. Okay, it's not going to let me do that. I'm going to say sometimes. So then we would convert that to a radical. We'd have to check that out. But so the computer can be somewhat helpful, and it'll show you some different ways to use that. But in that mode, there is polar form, there is imaginary A plus BI form, if you need to get that stuff in there.
Yep.
Okay, so converting from rectangular to trigonometric form, sketch a graph of the number x plus yi. This is going to be kind of important because you're going to need to know which quadrant you're in, and you'll be finding a reference angle. And then you're going to use that reference angle to find theta. So R is pretty easy to find. It's just the square root of x squared plus y squared, just the Pythagorean theorem. We're going to find theta by using the equation tangent of theta equals y over x. Now remember, if y over x is positive, it will give you, arctangent will give you a quadrant 1 angle, but it could be quadrant 3. You wouldn't know unless you draw the picture. If y over x is negative, arctangent will give you a 4th quadrant angle, but it might be a 2nd quadrant angle. So we did have to be kind of careful about that when we were finding the direction of our vectors. So as a caution, when you find theta, you'll only be given first or fourth quadrant answers. Make sure you adjust that so that you're in the proper quadrant.
Okay.
Okay, so write negative square root of 3 plus I in trigonometric form. We're going to use radian measure. So the first thing we're going to do is draw a picture. So we go negative square root of 3 units. So that's to the left square root of 3, up 1. And then to find R, we just take negative square root of 3 squared, which is 3, plus 1 squared is 1. 3 plus 1 is 4. Square root of 4 is 2. So that's how they got R to be 2 over here. So now we have 2 that goes in front of our parentheses for polar form. Next, we have to find theta. So when we do arctangent of 1 divided by a negative square root of 3, it's going to give us the fourth quadrant angle. Do you have your calculator handy?
Yeah.
Let's do second tangent, 1 divided by negative square root of 3. Make sure you're set to radian measure.
That's gonna be fun again. Trying to change all that. All right.
Okay, so when we do arctangent, and you probably get, and maybe degree measures better, because we can probably convert from degree to radians a little bit better than the decimal. So my calculator in degrees gave me negative 30 degrees, which is a negative pi over 6. So what they're saying is this angle here is 30 degrees or pi over 6. So we could take 180 minus 30 degrees to get 150, or a whole pi minus a sixth of pi would be 5 pi over 6. Did you understand what I was talking about the reference angle?
Yeah, I think so.
Do you need me to go back and go over that one more time?
No, sure, why not?
Okay.
Sure, I have it down.
Okay. Once we find R, we know that the tangent of theta is y over x. So in this case, that would be 1 over a negative square root of 3.
Yeah.
Which, after we simplify it, is a negative square root of 3 over 3. So using your chart, where is tangent equal to square root of 3 over 3? In radians.
It's pi to the 6th, but we're in the second quadrant, so you have to add.
So the reference angle is pi over 6.
Yeah.
But because we're in the second quadrant, we have to take a whole pi, because this is pi here, minus the reference angle. If we were in the third quadrant, we would have taken pi plus the reference angle. And if we were in the fourth quadrant, we would have taken 2 pi minus the reference angle. Clear as mud now?
What?
Is it clear as mud now?
Yep.
Okay, so here's the R we found is 2. Cosine of theta, which is 5 pi over 6. This should not be an equals, it's plus. I sine of 5 pi over 6. This is another way of writing that. 2, the R goes in front, cosine, I sine of pi over 6.
That must be declaring they're unlike of the 2 cosine by pi plus I sine.
Okay, write negative 3 in trigonometric form. You want to try this on your own? This is in degree measure.
I guess I can try it on my own.
Try it on your own. I'm going to try it.
Yep.
What would be the a plus bi form of this complex number?
It would be 0 minus 3i.
There you go. Okay, I just wanted to make sure you
So it's 270, isn't it? Because it's
Yes,
going
it is.
down.
Yep, that's 270. And R would be,
And R would be, I'm not sure, 3?
R is always the distance from 0, 0. So when you're on the X or Y axis, it's just how far you are from 0, 0. R would be the same as either X or Y, the one that's not 0.
Yeah.
Okay, so there's the picture. You're exactly right. Theta is 270. R is 3, the distance from the origin. So all we have to do is plug in R is 3, cosine of 270 degrees minus I sine of 270 degrees.
Yep.
Okay. Write each complex number in its alternative form using calculator approximations as necessary. So on this one, what is the reference angle of 115 degrees?
Well, it's 45, I'm thinking.
I think you're thinking of 215.
Yeah, probably. Let's see. Oh, it's 65.
It's 65. Now, is that an angle we know?
No.
No. So this one is we're going to use calculator approximations. So make sure your
Okay.
calculator is set to degrees. I usually just take 6 times the cosine of 115 and then 6 times I sine of 115 degrees. They have taken each one of these and then they're going to multiply by 6. I'm kind of lazy, so I just would do 6 cosine of 115 degrees, and your calculator should give you a negative 2.5357.
Yep, something like that. Looks like.
Yeah. And then for this part, I would have skipped the second step. I would have gone directly to 6 times the sine of 115 degrees, and it should give 5.4378. To me, it's just it's not hard to put in cosine of 115, but then you get all these decimals and you have to worry about round off error. So I like to skip those steps where you would be having to round when possible. All right, 5 minus 4i. Let's convert that to polar form.
All right. Does it matter if I have the calculator left in polar and a plus bi form?
It shouldn't unless you go to graph.
Okay. So that would mean that's going to go right, 5, and down 4. Something like that. So it's a pretty big old thing. It's going down 4 and it's going right 5. Okay. Let's see.
Is your sketch look somewhat like theirs?
Well, I got R. I was still trying to figure out how to get the
Okay.
angle. I wasn't sure how to get the angle.
Okay,
If you-
the angle is always going to be arctangent of y over x. So,
oh, yeah.
so arctangent of -4/5. We're fortunate, it gives us a fourth quadrant angle. So all we have to do is add 360 to make it positive.
Yep, add 360, and then the angle is 321 points, and depending on what they want to do. All right.
So I wrote the square root of 41 times the quantity cosine of 321.34 degrees plus I sine of 321.34 degrees, which is the same thing as square root of 41 CIS 324 degrees.
Yep.
Okay. Okay, the fractal called the Julia set is shown in the figure. To determine if a complex number z equals a plus bi is in the Julia set, perform the following sequence of calculations. So we've got z squared minus 1. We've got z squared minus 1, the quantity squared, minus 1. So what they're doing to get fractals, you keep substituting a function into itself. So they're putting z squared minus 1 in for the z to get the second one.
Okay.
And then they put it back in and they keep repeating that, substituting that in. If the absolute values of any of the resulting complex numbers exceed 2, then the complex number z is not in the Julia set. Now remember, the absolute values just mean the magnitude, or the a squared plus the square root of a squared plus b squared. Otherwise, z is part of this set, and the point AB should be shaded in the graph. So let's take a look here. Determine whether each number belongs to the Julia set. So what would be the magnitude, or I should say the absolute value of this complex number?
It looks like 0.
It looks like zeros. Don't you love it when you give you easy ones like that?
Yeah, makes life easy.
So that's the magnitude. But when we plug this number in, the magnitude is 0.
Yep.
So then we plug that into z squared minus 1. We get 0 squared minus 1, which is 0.
Okay.
So then we have to take that number and plug it in for z. The -1 squared is 1. 1 minus 1 is 0. Squared is 0 minus 1.
So will you always use this z squared minus 1 to...
Only for the Julia set. For the fractal that's a Julia set. You okay with that?
Yeah, I think so. And so you just continually place that in there to figure it out.
Uh-huh. So this time we got -1.
Yeah. And then you'll plug -1 into this one.
These are just going to repeat. So the absolute values are either 0 or 1, which do not exceed 2. So the point 0 plus 0i is in the Julia set, and the point 0, 0 is part of the graph.
Okay.
So if we put this diagram, and usually the x-axis, they would put probably the y is here, the x is there, and you can see 0, 0 would be in there.
Yeah.
Okay, what about 1 plus 1i? We're going to plug that in there.
Yeah.
So So we've got 1 plus 1i squared minus 1. What is 1 plus 1i, the quantity squared?
Would we FOIL that out?
Mm-hmm.
Yeah. That needs to be 1 plus 1i. So it'd just be plus 2i.
In there would just be plus 2i, but then we've got to subtract this 1. So when we put in the point 1 plus 1i, we get negative 1 plus 2i. And now we're going to put this in, negative 1 plus 2i. Oh, I forgot to tell the absolute values, the square root of 5. I just got that by taking 1 squared plus 2 squared, which is 5, and then taking the square root of that.
Why'd they do it there and not at the beginning with the 1 plus 1i?
Well, you have to plug it in first and then find it. On the previous one, they just said it was equaling the number 0. It just made it a little easier. Square root of 5 is greater than 2, so this is not in the Julia set. So we can stop there. As soon as you get a number, an absolute value that's greater than 2,
You just stop.
you just stop. It's not in the Julia set. So 1 plus 1i, we go back to this picture, and we don't know units on this. So this means that maybe this is 1 and then 1i might be up there. It's outside the black. Oops. And that was the application, and that ends it. That's kind of confusing, and I haven't done these problems this year yet, so I'll be working on them too. And but first, just make sure that you are able to convert rectangular to polar form and polar form to rectangular.
Okay.
Did you have any questions on college algebra?
No, not yet.
Not
I'm
yet.
in the practice quiz right now, so we'll see.
Okay. All right, well, I'll let you go ahead and get started with that. I think I said we'd connect. I'm just going to stay connected probably until 11.
All right.
So you can connect now, but if you plan on, if you have questions, just go ahead and connect again.
Okay. I shall.
All right, have a nice day.
You as well.